Trigonometric substitution. We often look for clever substitutions to make integrals easier. A powerful method is using a trigonometric substitution, or trig sub. Once we've exhausted all other methods, we often try trig sub when we see expressions like x squared plus a squared minus x squared, or x squared minus a squared, especially when they are under a square root. Here's a table to help choose the right trig sub. If you have the expression x squared plus a squared, you would substitute x equals a tangent theta. A squared minus x squared, you would sub x equals a sine theta. If you have x squared minus a squared, you would let x equal a secant theta. And here, a is a real number. You'll also need to remember these forms of Pythagorean identities. Tangent squared theta plus 1 equals secant squared theta. We'll use that with the first one. 1 minus sine squared theta is equal to cosine squared theta. This version will help us with the second one. And secant squared theta minus 1 is equal to tangent squared theta, which will help us with the third one. Something to keep in mind is that there are some restrictions. If we do a trig substitution, like let x equal a tangent theta, eventually we're going to have to return to x, and that's going to mean using trig inverse functions, and those have restrictions. So those restrictions are presented here, and we want to be careful when working with trig substitutions. Let's integrate 1 over x squared times the square root of 16 minus x squared dx. Keep in mind, we can't use substitution or integration by parts. This is an excellent candidate for trig substitution because I see an a squared minus x squared, and it's even underneath a square root. So that's the form that we're going to work with, a squared minus x squared. So the substitution is going to be a sine theta. So our a value is 4. We really have 4 squared minus x squared. So our substitution will be 4 sine theta. And so what we're going to do from here is we're going to take the derivative of that so that we get dx is 4 cosine theta d theta. And we can do a complete change of variables. We're going to replace each x and the differential dx with thetas. So let's go ahead and do that. We're going to have the integral of 1 all over. I'm going to replace x with 4 sine theta. Well, I have x squared, so 4 sine theta all squared is 16 sine squared theta. So I have 16 sine squared theta, and then times the square root of 16 minus another 16 sine squared theta. And I have to replace the dx with 4 cosine theta d theta. I'm going to put the 4 cosine theta in the numerator and then the differential in the back. All right, so now we start to simplify, and I am going to show all of the steps involved here on this first one, and then we can kind of try to shorten our work. So 4 over 16 is going to be 1/4, and I'll pull that out of the integral. In the numerator, I have cosine theta. In the denominator, I have sine squared theta times the square root of, well, there's a 16 in each term under the radical, so we can factor that out. And then I'd have the quantity 1 minus sine squared theta, and I still have d theta. So now the idea is that I should have underneath that radical a Pythagorean identity. So 1 minus sine squared theta is cosine squared theta. So now, let's see, the square root of 16 is 4. So I'm going to go ahead and multiply this 1/4 by another copy of 1/4. So I'm going to have 1 over 16, the integral of cosine theta over sine squared theta. Again, the square root of 16 was 4. We already dealt with that. And so we have the square root of cosine squared theta left over. All right, so the square root of cosine squared theta is technically absolute value of cosine theta, but because we work on those domain restrictions, since we had the substitution x equals a sine theta, we're on the restriction that theta is between negative pi over 2 and pi over 2. So we can go ahead and just assume this is the positive cosine theta piece. So I have 1 over 16, the integral of cosine theta over sine squared theta times just cosine theta. The square root and the squared cancel, which is often why we try trig sub when we see these types of expression underneath radicals. And then we still have that d theta. So now cosine theta divided by cosine theta is 1. And now I have more space, so let's go ahead and write 1 over 16. The integral of 1 over sine squared theta is cosecant squared theta d theta. Now, the antiderivative of cosecant squared theta is negative cotangent theta. So we have negative 1 over 16 cotangent theta plus c. But our answer is in terms of theta, and we need to go back and return to the x variable. So we're going to rewrite our substitution. X was equal to 4 sine theta. And let's go ahead and divide by 4 so that we could see that sine of theta is equal to x over 4. And we want cotangent of theta. So what we're going to do is construct a right triangle to find cotangent of theta. So here's my right triangle. And if sine of theta is x over 4, sine is opposite over hypotenuse. I want cotangent of theta, which is adjacent over opposite. Because let's remember, tangent is opposite over adjacent, and cotangent's the reciprocal. So if I can find the adjacent side, then I can replace cotangent theta with adjacent over opposite and return to the x variable. All I need is this missing side length of a right triangle, and we can find that using the Pythagorean theorem. Let's call that side length b for a moment. Then we know b squared plus x squared must be equal to 4 squared. So b squared is equal to 16 minus x squared, or b is equal to plus or minus the square root of 16 minus x squared. Don't do something crazy like take the square root of each piece. This is just the square root of 16 minus x squared, and we're going to take the positive version for this side length here, and because we know theta has our restriction, so 16 minus x squared underneath the square root. And again, cotangent is adjacent over opposite. So let's make that replacement. I have negative 1 over 16 times the square root of 16 minus x squared all over x plus c. And then we can rewrite this as negative the square root of 16 minus x squared all over 16x plus c. Let's integrate the square root of 9x squared minus 63 all over x dx. On this one, if we tried u substitution and let u be 9x squared minus 63, the derivative is 18x, and we don't have an x, we have a 1 over x, so that's not going to work. We're going to move forward with a trig sub, especially because we see these two terms underneath the radical, 9x squared minus 63. We do have a 9 in front of the x squared, and we can deal with that in a couple different ways. But on this one, notice that each term is divisible by 9, so we're just going to factor that 9 out to begin with. So that's the square root of 9 is what I'm factoring out, and that's 3. So I'm going to have 3, the integral of the square root of x squared minus 7 over x dx. So the substitution that we're going to make is of the form x squared minus a squared, and so x is going to be a secant theta. Our a value is going to be the square root of 7. 7 isn't a perfect square, but we can rewrite it as radical 7 squared. So our x will be the square root of 7 secant theta, and now dx will be the square root of 7 secant theta tangent theta d theta. So let's make our replacement. We're going to go ahead and have 3 times the integral of the square root of x squared. Well, x is radical 7 secant theta, so that's going to be 7 secant squared theta minus 7 over x, which was the square root of 7 secant theta. And we don't want to forget to replace dx. dx is the square root of 7 secant theta tangent theta d theta. All right, a couple of nice things happen. So the square root of 7 over the square root of 7 is 1. Secant theta over secant theta is 1. So now underneath the square root here, I have two terms with the 7 in common. So I'm going to factor out the 7 and so take out the square root of 7. So here's where I'm at. I have 3 times the square root of 7, the integral of the square root of secant squared theta minus 1 times tangent theta d theta. And then really just over 1. Well, secant squared theta minus 1 is tangent squared theta. So I have 3, the square root of 7, the integral of radical tangent squared theta times tangent theta d theta. The square root of tangent squared theta is just tangent theta under the restricted domain. So we're going to have a tangent theta times a tangent theta for a tangent squared theta as the integrand d theta. Now, this doesn't have a general antiderivative, so here we go again with those Pythagorean identities. Let's rewrite tangent squared theta as secant squared theta minus 1. Secant squared theta does have a general antiderivative, tangent, and then we'll have minus theta. So we have 3 times the square root of 7, then we have tangent theta minus theta plus c. All right, so now we need to get back to x. So let's remember that our original substitution was x equals the square root of secant theta. So x over radical 7 is equal to secant theta. Now for this one, tangent theta is opposite over adjacent. So we're going to construct another triangle and figure out what that relationship is going to end up. So if we construct our triangle here, a right triangle, secant of theta is x over rad 7. So secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. So this is x, and then rad 7 is the adjacent side. And so I'm missing the opposite side. Let's go ahead and call that b. So b squared plus radical 7 squared equals x squared. So b squared is equal to x squared minus 7. So b is equal to plus or minus the square root of x squared minus 7. All right, so now let's replace b with the positive version of that based on the domain restrictions, x squared minus 7. And then tangent of this angle theta is opposite over adjacent. So we can return the first piece to x. 3 times the square root of 7. Tangent is opposite, radical x squared minus 7 over adjacent radical 7. But now we have minus theta, just theta. So here, when I have x over radical 7 equals secant theta, what I can do is take secant inverse of both sides. So I can go ahead and say that theta is equal to secant inverse of x over radical 7. And now I can write theta as a function of x. Kind of an ugly one, but it works. We could also, if we don't want secant inverse, it's still going to be kind of ugly, we can write this as cosine theta is radical 7 over x, the reciprocal. And then we can say theta is cosine inverse of radical 7 over x. Either one is fine. I'm going to go with the cosine one just because I think cosine inverse is a little nicer than secant inverse. So I have cosine inverse of radical 7 over x plus c. Now, one last thing, I'll distribute the 3 radical 7, especially because here I'll notice that they cancel out. So I'll have 3 times the square root of x squared minus 7 minus 3 rad 7 cosine inverse of radical 7 over x plus c. Let's integrate x squared all over the quantity 4x squared plus 1 squared dx. We are going to use a trig sub, even though we don't see a square root involved. It doesn't have to have that. If we tried another method like u substitution, with u is 4x squared plus 1, the derivative is 8x, and we have an x squared, so that's not really going to work. But we do see this x squared and this a squared. There is a 4 in front of it, but we're going to move forward with a trig sub, and the sub is x squared plus a squared. And so we know that x must be a tangent theta. All right, but I already said we don't quite have x squared, we have 4x squared. And we can't factor a 4 out of here. Well, we can, but it's going to leave us with some fractions. So what we can do instead is think about 4x squared as 2x quantity squared. So in other words, I can think about this as x squared over the quantity 2x squared plus 1 squared dx. And then I'm going to let 2x be equal to a, which is 1, so 1 tangent theta. So in place of x, I have a 2x. So in my substitution, I'm going to let my x be a 2x. So 2x is equal to tangent theta. So that means that x is 1/2 tangent theta. And then dx is 1/2 secant squared theta d theta. So now we can make our substitution. So x, we did solve for just x when we divided by 2. X is 1/2 tangent theta. So x squared is 1/4 tangent squared theta. So we have 1/4 tangent squared theta in the numerator. In the denominator, 2x is tangent theta. So 2x all squared is just tangent squared theta. So we have tangent squared theta plus 1 squared. And then dx was 1/2 secant squared theta d theta. All right. So now I have 1/4 times 1/2 is 1/8. Let's bring that out. So I have 1/8, the integral of, I have tangent squared theta, I have a secant squared theta, all over tangent squared theta plus 1 is secant squared theta, and that's all squared, so I have secant to the 4th theta d theta. All right, well, some nice stuff happens. Secant squared cancels with 2 of the copies of secant on the bottom, so I'll have a secant squared left on the bottom. And so I have 1/8. The integral of tangent squared theta is sine squared theta over cosine squared theta. And instead of dividing by secant squared, I can think about dividing by 1 over cosine squared, which is multiplying by the reciprocal, cosine squared theta over 1. All right, and cosine squared theta over cosine squared theta is 1. So what we're integrating here is just sine squared theta. We know to use the power reducing identity here. So I have 1/8, the integral of 1 minus cosine 2 theta over 2 d theta. I'll pull out the 1/2, so I have 1 over 16. the integral of 1 minus cosine of 2 theta d theta. The antiderivative of 1 is just theta. And then the antiderivative of cosine 2 theta is going to be 1/2 sine of 2 theta plus c. All right, so now we got to get ourselves back to x. Let's remind ourselves, originally we said 2x is equal to tangent theta. So here, if we want to go ahead and replace theta, we can take tangent inverse of both sides. So we know tangent inverse of 2x is equal to theta. So we can make that replacement. So we can say 1/16 and then tangent inverse of 2x. And then here, what I don't want to do is substitute in tangent inverse of 2x right here into this theta and end up with a composition of sine of tan inverse, or sine of 2 times tan inverse. I don't want to make something that ugly. So what we're going to do instead is use the double angle identity that I see here. So I'm going to leave the 1/2 and remember how sine of 2 theta is 2 sine theta cosine theta. So how does that help us? Well, 1/2 times 2 is 1. And now I can replace sine theta and cosine theta to be functions of x. It relies on me going back to this original relationship, 2x is equal to tangent theta, and drawing a triangle. So I have, this is really 2x over 1. So let's construct our triangle, our right triangle. Here's theta. Tangent is opposite, 2x, over adjacent, 1. So we're solving for the hypotenuse this time. Let's call it c, or c1, because I don't want to confuse it with the constant c. So I know that 1 squared plus quantity 2x squared is equal to c1 squared. So that's 1 plus 4x squared is equal to c1 squared. If I take the square root of both sides, I get plus or minus the square root of 1 plus 4x squared is equal to c1. Well, I'm going to take my hypotenuse to be positive. So I have the square root of 1 plus 4x squared. And now sine of theta is opposite over hypotenuse. So I can replace sine with opposite 2x over hypotenuse, radical 1 plus 4x, times cosine theta is adjacent over hypotenuse. So 1 over the square root of 1 plus 4x. Whoops, I lost the squared on both of those. And then we'll just bring down tan inverse of 2x. And this was all times 1/16. And then plus c. We can clean it up a little bit more. I needed a little more space. So I'm going to write 1/16 tan inverse of 2x minus, okay, so if I multiply 1/16 times this 2, that's 1/8. And then these multiply together, and so the two square roots cancel. So I'm going to have an x over 8 times the quantity 1 plus 4x squared plus c. So one of my terms does have a trig inverse function, but the other term is now a really nice algebraic function. Here, let's integrate x squared dx over the square root of 4 plus x to the 6th. This has a really different look to it. The trig sub that we're thinking here is a squared plus x squared. And of course, that becomes x equals a tangent theta. And the part underneath the square root doesn't quite have that look, but if we rewrite it as 2 squared plus x cubed squared, then we start to have that form. And so what that would mean is that I have to let my trig sub be x cubed is equal to 2 tangent theta. And let's see where it goes from here. So let's go ahead and take the derivative of both sides. So 3x squared dx is 2 secant squared theta d theta. Now here that helps us because we have x squared dx to change into thetas. So we'll just go ahead and divide by 3. So we know x squared dx is 2/3 secant squared theta d theta. So we have enough to start making our replacements here. So we're going to say that the numerator becomes 2/3 secant squared theta d theta over the square root of 4 plus, all right, remember that x to the 6 was x cubed squared, and x cubed was 2 tangent theta, so we're looking at squaring 2 tangent theta, which is 4 tangent squared theta. All right, so now let's pull the 2/3 out to the front of the integral, and what's going to join it is a 1/2, because I can pull a 4 out here, and then the square root of 4 is 2 in the denominator, so I'm going to have a 1/2 the integral of secant squared theta d theta over the square root of 1 plus tangent squared theta. So 1 plus tangent squared theta is secant squared theta, and it's underneath the square root, so the square root of secant squared, because of domain restrictions, is just positive secant theta. And I have secant squared on top, so that's just going to simplify to 1 copy of secant theta. So as we start to move through these problems, we can work a little quicker in identifying how things are going to simplify. So we have a 1/3, and we're really just integrating secant theta d theta. All right, so the integral of secant theta is natural log the absolute value of secant theta plus tangent theta plus c. And now we get ourselves back to the x variable. So we have that x cubed equals 2 tangent theta. Well, that means that x cubed over 2 is equal to tangent theta. Well, look at that. I can make one replacement automatically. But to find secant theta, I'm going to draw a triangle. So we have our triangle here, our angle theta. Tangent is opposite x cubed over adjacent 2. And so this missing side length here, we want to be able to identify what this is a little bit quicker. So it's going to be each of these sides squared, added together, and underneath a square root. So 2 squared is 4, x cubed squared is x to the 6th, 4 plus x to the 6th underneath the square root. So we have the square root of 4 plus x to the 6th. Oh, hey, what do you know? It's the same piece that was in the original integrand, and that's not a coincidence, right? That's definitely going to happen if you go back and check the previous examples. So we want to try to get pretty good at the mental math involved in finding the missing pieces of a right triangle. So now secant is the reciprocal of cosine. So instead of adjacent over hypotenuse, it's going to be hypotenuse over adjacent. So we're going to have 1/3 the natural log of the hypotenuse 4 plus x to the 6th over the adjacent side 2 plus, again, tangent theta was just x cubed over 2 plus c. And these have common denominators, so we can write it all as 1. So here we have our final answer. Now let's work on a definite integral involving trig sub. The integral from 1/2 to 1 of the quantity 1 minus x squared all to the 3/2 over x to the 6 dx. We do have an a squared minus x squared, where a is 1. And even though it's not written as a radical, it can be written as a radical, this exponent of 3 over 2. So our substitution is going to look like x equals 1 sine theta, then dx is cosine theta d theta. But because we have a definite integral these are x values, and we're going to want to change them to theta values. So here, if x is 1/2, I'm going to go ahead and try to solve for theta within my domain restriction. So I have 1/2 would be equal to sine theta. Obviously, there's a lot of solutions, but between negative pi over 2 and pi over 2, the only solution is pi over 6. And then if x is 1, go ahead and do that work. If x is 1, then what is the angle theta between negative pi over 2 to pi over 2? That's going to be pi over 2. So theta is going to be equal to pi over 2. Let's rewrite our definite integral as the integral from pi over 6 to pi over 2. In the numerator, I'm going to have 1 minus x squared. X was sine theta, so sine squared theta to the 3/2. And then x to the 6th will become sine to the 6th theta. And then dx is cosine theta d theta. 1 minus sine squared theta is cosine squared theta. So I have pi over 6 to pi over 2. I have cosine squared theta to the 3/2. And then over sine to the 6th theta times cosine theta d theta. And now let's go ahead and see what we have. So cosine squared to the 3/2 is going to just give me cosine cubed theta. So 2 times 3/2 is just 3. And then there's this extra copy of cosine over here, so that's a total of 4 copies of cosine. So I have the integral from pi over 6 to pi over 2 of cosine to the 4th theta over sine to the 6th theta d theta. Now this is kind of an interesting one to evaluate. So here what we're going to do is we're going to rewrite the integrand as cosine to the 4th theta over sine to the 4th theta times 1 over sine squared theta d theta. And hopefully you can see what's going to happen. Cosine over sine is cotangent, so we're going to have cotangent to the 4th theta, and then times 1 over sine squared theta is cosecant squared theta d theta. And there's a really nice u substitution that we're going to be able to do from here. If I let u be cotangent theta, then du is cosecant squared theta. I really want to make sure this looks like an exponent here. So this should be cotangent to the 4th theta. All right, so let's let u be cotangent theta. Du is negative cosecant squared theta d theta. Multiply the negative over to the other side. Okay, well, now our limits of integration need to change again. They are theta values, and they're going to need to become u values. So if I substitute in pi over 6 into cotangent, cotangent of pi over 6 is the square root of 3. And if I substitute in pi over 2, cotangent of pi over 2 is equal to 0. All right, so now what's going to happen? We have this negative, so I'm going to keep the negative on the outside. Pi over 6 corresponded to rad 3. Pi over 2 corresponded to 0. And then I have u to the 4th du. Let's flip these limits of integration so I can get the smaller one on the bottom, and then that will get rid of this negative. So I have the integral from 0 to rad 3 of u to the 4th du. We're in the home stretch here. We're going to take the antiderivative as 1/5 u to the 5th, evaluated from 0 to rad 3. Now I'm going to plug in rad 3, raise it to the 5th power, minus, plugging in 0 doesn't do anything. And the square root of 3 to the 4th, that's going to give me 9. So I'm going to have 9/5 rad 3 as my answer. Now let's find the integral from 1 to 2 of dx over x times the square root of the quantity 25x squared plus 4. So here, the part underneath the square root that we're going to focus on is 25x squared plus 4. And we have that 25 in front of x squared, So we want to think about it as quantity 5x squared plus 2 squared, so that we can identify that the trig sub we're going to do is that 5x is going to equal 2 tangent theta. Well, let's go ahead and divide by 5. So x is 2/5 tangent theta. And then dx is 2/5 secant squared theta d theta. Now we have all the pieces to replace the integrand and the differential, the x squared, the dx, but the limits of integration are still x values. So if I let x equal 1, then I'm going to have 1 equals 2/5 tangent theta. Let's multiply both sides by 5/2. So I have 5/2 equals tangent theta. And this isn't a nice angle on the unit circle. I don't know what to plug in to tangent to get out 5/2 in our restricted domain values from -π/2 to π/2. So I'm actually going to take tan inverse of both sides so that I get tan inverse of 5/2 is equal to theta. And that's going to correspond to the lower limit of integration. And I'm going to do the same thing for the upper limit of integration. 2 must be equal to 2/5 tangent theta. So multiplying by 5/2 on both sides, I'm going to get 5 equals tangent theta. So tangent inverse of 5 is equal to theta. All right, let's make all of our substitutions now. I'm going to have the integral from tan inverse of 5/2 to tan inverse of 5. dx becomes 2/5 secant squared theta d theta all over. We can replace x with 2/5 tangent theta. And then underneath the square root, 25x squared, remember it was quantity 5x squared, and quantity 5x is 2 tangent theta. So if we square 2 tangent theta, we're going to get 4 tangent squared theta. So 4 tangent squared theta plus 4. All right, let's do some simplifying here. We have the 2/5 over 2/5 is 1. And then underneath the square root, I can factor a 4 out, and then the square root of 4 is 2. So I can pull a 1/2 all the way out of this. So I'll have 1/2 the integral of tan inverse of 5/2 to tan inverse of 5 of secant squared theta d theta over tangent theta. And then underneath the square root, I'll have left tangent squared theta plus 1. Well, tangent squared theta plus 1 is secant squared theta. And we're taking the square root of secant squared. So we are going to have just secant theta. And that's going to cancel with one of the secant thetas up here. And so we're going to end up with 1/2 the integral from tan inverse of 5/2 to tan inverse of 5 of just one copy of secant theta on the top, and then one copy of tangent theta in the denominator. All right, so now let's try to simplify the integrand. We're going to have 1/2. Here are our limits of integration. And then secant is 1 over cosine theta. And then instead of dividing by tangent, which is sine over cosine, I'll multiply by the reciprocal cosine theta over sine theta, d theta. Now, the cosine thetas cancel and give us just a 1, so I have 1 over sine theta left, which is cosecant theta. And we do have our antiderivative of cosecant theta usually memorized. We have some more space here. We'll write this as 1/2 the integral. We have some more space here. We'll now write 1/2, and then the antiderivative of cosecant theta is negative natural log cotangent theta plus cosecant theta. And this is evaluated from tan inverse of 5 over 2 to tan inverse of 5. So we're going to have some really ugly answers. We are going to just go ahead and substitute in those quantities. So tan inverse, cotangent of tangent inverse of 5 plus cosecant of tangent inverse of 5, and then minus a negative, so plus natural log of cotangent of tangent inverse of 5 over 2 plus cosecant of tangent inverse of 5 over 2. All right, so this big long thing is the answer, and there is more simplifying we can do, so let's go ahead and do it. So here, cotangent of tangent inverse of 5, these don't directly cancel, cotangent and tangent inverse, but they do cancel and become the reciprocal of this value here. So cotangent of tan inverse of 5 becomes 1/5, and cotangent of tan inverse of 5/2 becomes 2/5. And then cosecant of tangent inverse of 5. So to simplify this composition, I can create a triangle. So I can say, well, tan inverse of 5, that's some angle theta. And then this problem is really asking me to do cosecant of theta. And tangent of theta then must be equal to 5 over 1. So we'll construct a right triangle with an angle theta, and tangent is opposite over adjacent. So the hypotenuse is the square root of the two side lengths squared and added together, the square root of 26. So this expression is really asking us for cosecant of this angle theta, which is the reciprocal of sine. Sine is opposite over hypotenuse. So we're looking at hypotenuse over opposite. So the square root of 26 over 5. So this entire expression, I'm going to erase my scratch work here. This entire expression is the square root of 26 over 5. And remember that these are added together inside these absolute value bars. And then in a very similar way, I can find that cosecant of tan inverse of 5 over 2, setting up another triangle, would give us, I'm going to skip a little bit of work here, the square root of 29 over 5. And again, these are added together. So here's what we have. I'm going to have 1/2 negative the natural log of 1 plus rad 26 over 5 plus natural log of 2 plus radical 29 over 5. So I have this logarithm here, this natural logarithm here, minus this natural logarithm here. And hopefully we remember a log property that says I can combine these to be a quotient. So I'm going to have natural log of this argument, this inside here, over this one. So that's going to leave me with 1/2 natural log, the absolute value, 2 plus rad 29 over 5 over 1 plus the square root of 26 over 5. All right, well, they're both divided by 5. So if I multiply by the reciprocal, I would see that those cancel. So my final simplified answer here is 1/2 natural log of 2 plus the square root of 29 over 1 plus the square root of 26. Whoops, I was about to put plus c, but this is a definite integral. So that's it. That is the answer. So this was definitely trig heavy, but we are doing trig substitution with a little bit of log properties. Now, just because we see the sum or difference of an x squared and an a squared, that doesn't necessarily mean we're going to jump straight to trig sub. We're going to look at our integrand and think about what other integration strategies we have first, because trig sub, while beautiful, takes a lot of work. So this first one, the integral of x over the square root of the quantity x squared plus 4 dx, we can actually apply a traditional u sub. Let u be x squared plus 4, and then du is 2x dx. And we can see that we have an x dx, so just a little bit of rewriting here, and we can complete this as a u sub. Now, for the next two, we want to be able to just recognize the form so we can jump straight to the answer. The integral of 1 over the quantity x squared plus 4 dx, that one automatically becomes arctangent. I have 1 over x squared plus a squared. So it's 1 over a, or 1 over 2, arctangent of x over a, or x over 2 plus c. We could have done a trig sub, would have been way more work. And then same thing with the last one, the integral of 1 over the square root of 4 minus x squared dx, that one's going to become arcsine. So that one does not have 1 over a in front. It just simply becomes arcsine of x over a, so x over 2 plus c. So don't trig sub everything that has the sum or difference of an x squared and an a squared.